Good morning to everyone. I'm Amulya Marali, AI Research Intern at Cellstrat. Today I'll be taking a webinar on understanding AI image generation, and now I'll get started with the presentation. So yeah, understanding AI image generation. Now we know the buzzwords: Stable Diffusion, DALL 2, Midjourney, and so many more. So how do these things actually work, and what is the algorithm behind it? And even before we came to the algorithm behind these very much in use terms, what were the the models or the algorithms that were before the present master, anything as such? So let's get started from the scratch, and what came first, second, and then why they didn't perform that well. So why the present model's algorithm is being used and all of that. So coming to the table of contents with today's webinar, we will first start with GANs and VAEs, which are some of the few initial or the initial image generation algorithms. And then due to a few flaws in them, we had to come up with something new, that is diffusion model. And from diffusion model, something called as latent diffusion model. What is it? What is the difference between these two diffusion models? And then let's talk about few state-of-the-art models, such as diffusion, stable diffusion, DALL 2, Midjourney. And let's try to compare depending on if we get the time. And then let's not miss on the code demonstration for stable diffusion, where we put in text prompts and understand how things work. And yeah. Now, starting from generative adversarial network. So let me just put this in this way. Generative adversarial networks has two models or submodels. First is generator, and then comes the discriminator. The word adversarial itself states that there is some conflict between these two models, and by the way, they are CNNs. So what actually happens here, and how do these models, even though there are conflicts, work together in order to generate images, and how all of this happens? Let's understand. Now, coming to discriminator model. Let's first take an example of generating flower images. So here, let's keep the generator model as of now frozen, meaning we're not working or doing anything to the generator model. Let's just keep it aside. Now let's work on the discriminator model. Like how we train any CNN, any simple CNN of classifying or recognizing images. Let's do the same thing and train our model with multiple image data of flowers and train it in a way that it can identify or recognize a flower input. Any input or an image of flower, it is able to recognize it. And also make sure that it doesn't recognize any non-flower images, meaning it recognizes the non-flower images as not a flower. So now the discriminator model is ready. Now let's come to the generator model and make sure that generator model starts generating few fake images of flower. And that fake image of flower that generator model has generated will be passed on to the discriminator model. Now what happens is that discriminator model is given this, it has to predict whether the input that it is given, whether it is a flower or not. Based on its training, for the first for the first image generated by its generator model, let's take it this way, that it identifies or discriminates it as not a flower. So the generator model has not done a good job here of generating a fake flower image, which couldn't be recognized by the discriminator model. So what happens? This is something that is not good for the generator model. So it goes back again and it updates the model. So any the losses or the weights, all of that are taken into consideration, and then the generator model is updated to perform well in the next whatever image it generates. So now, because the discriminator model identified the flower that the generator model generated as not a flower, the generator model had to do some homework in updating the model and performing well for the next output. So again, the generator model generates some image of flower, and now the discriminator model, the model's job is to identify whether it's a flower or not. But this time, let's say that the discriminator model actually failed to identify the fake flower as not a flower, and it was fooled in a way that it was identifying the fake flower as a flower. Now what happens? Now it is time for the discriminator model to update itself and make sure it identifies fake flowers or flowers as in the proper way. So this happens until and unless the discriminator model is fooled completely, meaning generator model generates images in such a way that even the discriminator is not able to understand whether it is fake or not. Through this whole process or the method, we generate images just by text prompts, where it can be taken into such an extent that even such models are not able to identify whether they're fake or real. So this was one of the image generation algorithms or model which were used before. And let's also go to the problems that they faced later. And now we will talk about variational autoencoders. So what happens here is that there's basically something called as autoencoder and a variational autoencoder. But before going to variational autoencoder, let's talk about what happens in autoencoders. You have an encoder and a decoder. What encoder does is that any information you pass, it encodes it or compresses it in a form that later decoder decompresses it and produces an image. So there are situations where everything that you compress will not be decompressed back to the original image. There will be some losses that can be taken into consideration. Because of such losses that can be seen, or even compressing images to an extent where later it is extremely difficult or not feasible in order to decompress it back, we had variational autoencoders coming into picture. So again, in autoencoders, what happens is that we cannot guarantee the regularization, meaning the data can be overfitted or underfitted. These terms that we know, where the model can learn a lot of these parameters, and when it has to apply it to the actual image, it makes or it goes wrong, because what it did, it just studied whatever. Okay, in other if I had to explain it in a different way, if you have to write a test, you just studied everything, each and every line from your textbook. But what you're not able to do is apply the same content that you studied in a different way. It is the same thing, but you're not able to understand how to apply it. That's where the overfitting comes, and similarly underfitting. That's why autoencoders, you cannot guarantee regularization in the training process. That's what the limitations of autoencoders, which led to the variational autoencoders to come into picture. Here, what happens is that you have a latent space concept coming into picture. So dimensionality reduction, that is, when you compress the data, it is compressed into a latent space. So when you compress it, decompress it back, you don't have such problems being fixed. Now coming to the advantages and what these three models do.
Yeah, I think let's open to some questions periodically. So, audience, I know there is a lot of content being presented. So, if any questions or comments, do let's make it interactive.
Yes, sir. But the comments are not able to see here because I'm not on Gmeet.
That's fine. So, no audience can speak out their questions, or if they choose to put it in chat, I can recite them. So we have already discussed GANs and autoencoders, folks. So, any questions so far? And these are all image generators, right? So
Yes.
these are all image generators. Okay, I guess we can continue.
Sure, sir.
I guess you're going a little fast. Let's slow down a bit.
Okay. Cool.
Prompt audience for questions.
Okay, sir. Okay. So here, this is from a NVIDIA developers blog, this image, which actually explains what these different algorithms have as an advantage. So when it comes to GANs, you have fast sampling or high quality samples. Then when it comes to variational encoders, you again have fast sampling, mode coverage and diversity. And then denoising diffusion models, again high quality samples and mode coverage and diversity. But even after having such advantages, there are few disadvantages that GANs and VEs faced. That's why that led into the um, uh, the finding of diffusion models. So let's understand the problems. So basically, what GANs actually faced is mode collapse problem. So what happened here is that now just imagine if the generator model identified that one flaw or that one data point that the discriminator model is not able to recognize, meaning it would generate images in certain data parameter that the discriminator model is not properly trained on. So which means that it is not able to detect the fake image. Even though it is fake, it is not able to detect only because it is in that line. So it's only one hole or a loophole that the generator model has found, and it's producing image only in those or in that perspective. But this generator model is actually not being trained properly. It has found a loophole and it's trained and it's producing generating images only in that line. So it is of no use at the end of the day, because even though your discriminator model is not able to detect the thing, only because that one line is the problem. At the end, when you have results saying that it has failed completely, or generator model has fooled the discriminator model, the only problem we face is that we don't have a successful model at the end of the day because of this mode collapse. So again, that one flaw, or if it finds it, it will start generating images in only that line. That's again another problem. So because of it's difficult to train at times because of these reasons and many other things, and also the drawbacks in VAs of blurry outputs. We came up with something new, that is the diffusion model. So diffusion model, again, it's a very beautiful concept. So what happens here is the two-stage process that comes into picture. So you have two stages here. First stage is forward diffusion. And let's understand what happens in forward diffusion, and also eventually come back to reverse. So now let's take that you want to train it, or okay, so what actually happens here is an image you take and you start adding noise in subsequent stages. So for example, here, let's take an image of cat, and we will start adding noise one by one, noise at every stage. So we have to follow a method or something in order to add noise. Adding noise, what does it actually mean to add noise? So what we will be adding here is Gaussian noise. In what process? In Markov chain process. So what is Markov chain basically? So it's a stochastic model, meaning randomness. So what it does is it basically identifies what the next instance or next output is going to be, depending on the present or the previous the input. So based on what is there now, it can detect the next thing. So this is just a very uh, what simple terms explanation of what Markov chain does, and then the Gaussian noise. So now let's understand how Gaussian noise actually works in order to add noise to these images and the equation of course. So now coming to x and xt and xt minus 1. So we actually take x as the initial image added to the forward process. So x is the initial or the original image. So xt, t is basically at any given timestamp or time, the image present is xt. So then xt minus 1 is the image just previous to the present timestamp of the time. And then coming to the right hand side of the equation, which is again the Gaussian noise equation, we have two what variables, or variables, yeah, actually variables, mean and variance. So what actually happens in these two, and what is this beta, and what is this whole equation? Let's understand that. So coming to variance schedule, what it does. Now, how will we get to know, or how will the model or anything that is monitoring this get to know how much noise has to be added at each step? In order to understand that, or in order to take decisions on that, we have something called as variance schedule. So now coming to beta, which actually plays this or is an important thing in deciding how much noise has to be added or not. Beta, basically, this beta will take care of all that. So let's understand what the role of beta is. So now we already got to know that variance schedule, that is nothing but beta, takes care of how much noise has to be added at every stage. Now, what will happen if beta is extremely high or extremely low, or what is that point where, or what is the exact value of beta that has to be taken into consideration in order to add some optimum amount of noise or anything as such? So let's just consider that beta is extremely high. So what this happens is that the variance will be again at its max. If you take beta more and more and more, variance will increase eventually because it's a directly proportional relation here. So which also means that the pixel distribution will become wider, again because of the greater variance. But this also means that mean, which is in this equation, that is root over 1 minus beta t into xt minus 1, will decrease eventually because it's 1 minus a larger value, and it will go to a point where it will become 0. So the curve or the normal curve eventually shifts towards 0. So this
Yeah,
corrupts the.
yeah. So I had a question. So this is a Gaussian probability distribution,
Yes, sir.
and so we are trying to go from image to noise.
Yes, sir.
So that's a very counterintuitive viewpoint. Why would we want to produce noise from an image?
Huh.
And by sampling xt from the previous xt minus 1 using a Gaussian probability distribution.
Yes, sir.
When that
But what is the, because this is only the forward process where we are adding noise.
why we are adding noise
Hmm.
using a Gaussian probability distribution? Why would somebody want to produce noise from an image?
Huh. We are producing noise from an image. I mean, not producing noise, but adding noise to the image to take it to a certain extent where it is not recognized at all. The reason why we're doing this is because when we add the denoising algorithm later, we have to see whether we get back the same image or not. So trying to generate a different image from an already present original image. Okay, you have different conditioning that will cover later, that is image to image, text to image, all of that. But generating an image from already present image by adding noise and then denoising it.
So
This
we
is the
are
whole
going
process.
from image to noise,
Hmm.
and then we will train a backward model
Yes, sir.
from noise to image.
Yes, sir.
So the encoder is image to noise, and decoder would be noise to image.
Yes, sir.
So in that way, that is similar to a UNet or autoencoder.
Huh.
Uh,
So I'll.
so the final goal is to discard the encoder
Hmm.
and then use the decoder, which is a noise to image generator in production.
Yes, sir.
So given noise, you will be able to produce remarkable images. So that's the final goal, I guess, right?
Yes, sir. That's the goal. So we are working towards generating images from the already present image through these two processes. Now, why we are adding noise and why we're removing noise, you'll understand eventually. So yeah, now coming to, we went a little in depth into the equation, how noise is added from the previous. So basically, if I start with a cat image and then at step zero was my cat image. Step one becomes still a cat image with some noise. But this cat image's noise that we generated or added in step one is dependent on step zero. Similarly, step two's noise that is being added and generating a cat image which is with more noise depends on step one's cat image, which has some noise. This is how the Markov-Chan algorithm is being deployed here. At the same time, generating noise at each step and adding noise depending on parameters like beta and also with respect to previous noise image. So we'll take into consideration that we're doing it for some 200 steps, and 200th image is this image which I cannot even tell it's a cat because that's that much noise is there in it that no one can say that it's a cat or a dog or it's a human, nothing. It's just noise and nothing. So we understood what is beta. So now how to determine this beta value that we had this question. Okay, there are many noise scheduling techniques or methods. Uh, so some of them were linear, sigmoidal, and quadratic. I'll not go too much in depth into this thing because it does require a lot of understanding. And coming to why we need this beta and why we are using beta or these scheduling techniques is because this allows the denoising process to function well. In other terms, you are adding this noise, but later when you have trained another model to predict the noise at every instance, it would become make the job of that denoising algorithm to predict noise when you're using such scheduling algorithms. So yeah, now the question is, now we have generated this, completely cluttered image with a lot of noise. How are we coming back to this original image? This is where the reverse diffusion comes into picture. That is, we are recovering the image that you initially had from the noise that you created. Okay, just to divert back a little and to make it feel even more, beautiful enough, the concept. So I remember reading this somewhere where you just take a glass of water and you drop some essence or some colored dye into it. So eventually you will see that the water becomes or it eventually takes the color of the dye that you had put or the drop of impurity, whatever it is. The thing is that you don't know where the drop of impurity is actually put initially. But what you can see is that it has generated this water, or at the end, you have this glass full of dirt or impurities. Initially, it was just clear water, and you added some drop of some impurity in it. And eventually, you found, and at the end, you had this glass of water with complete impurity or whatever. The question is, how to find, or if you want to find where the drop of impurity was added. You don't know where it was actually added, but it was added. So this reverse diffusion and this denoising algorithm will exactly or it will try its best to tell where that drop of impurity was actually added in order to produce that noise. So I think it's exciting enough to find that initial spot of noise that you started creating from all the noise that you got, and this process how it's done. Because okay, now I'll actually explain how it is done. So coming to the neural network behind the prediction of noise. So we make use of UNet here, and I'll tell you eventually why UNet. And before UNet, we train these models on different images and their captions. And for that, you have this data set called as LAION 5D, which is publicly available. And yeah, we'll see how we will make use of this noise prediction algorithm or model or neural network in order to get back our initial or the original image from the noise that it has been created. Any questions so far before we get into the process? Mm, okay, then I'll take it as a no and I'll go forward. Okay, so how training is done in this reverse diffusion model. So as I told you, we'll be making use of UNet model and I'll eventually explain in simple terms what UNet actually does. But before that, let's just start with the whole, if you want to like train your a diffusion model, how do you actually do it? So now just pick a image of cat. Okay, then you start generating random images like you can see in this step. Eventually, it's at the fourth step, you have nothing but just noise. How you do it, as I explained before, using Gaussian noise. And then what later that comes is you teach your noise predictor to tell how noise is added, which eventually starts predicting noise at every step. So UNet is an already trained model that knows at what point the noise will be, or at what point the noise is. And using this, I'll tell you what we'll do. So now coming to how the noise prediction is actually done. If you see this image, it's a very wonderful, easy to understand depiction of noise prediction. So at this step, I hope the pointer is like clear here. So this is the image that you generated from the forward diffusion process. That is nothing but just noise. And you are deploying this prediction or predicted, noise prediction in order to predict noise at this point. So 200th image has some noise. It is nothing but noise again. But what was that amount of noise that was added from 199th image to the 200th image? That gap or that whatever difference is, we will try to predict it using this noise prediction algorithm or unit basically. So that predicted noise is subtracted from the 200th image, and later you eventually generate your new 199th image. And you do the similar thing, you iterate towards the whole thing. You just go on subtracting, basically predicting the noise at that point, subtracting it from that, and generate the new thing, again predicting, subtracting, until you get this image of the cat.
So
So
one question I have is, will it predict will it predict very precisely similar images as the from where it started, went to noise, and now you're coming back from noise to image,
no, sir,
or it will create variations in images?
we will for sure have variations. We cannot generate a completely similar image that we had before. That's why generation comes into picture, where you're not generating the same thing, but something different but similar. So the noise that you added, and because you'll have many losses here in between these many uh, the predictions in the neural networks. So
Like new, so some examples could be new fashion design, right?
yes, sir.
Similar to existing fashion, but slightly different,
Yes, sir.
or new shoe design, or new interior design for houses, and so on, right?
Yes, sir. So actually, that's why we make use of these methods in order to create our own data set. So it's also saying that within a few years, you will not have any artists or any such professions being paid enough, or it will just disappear, because such models, such AI is coming into play, and they are just taking the world. You can do everything when you have such intelligent algorithms being deployed and a lot more.
So there is one question on chat, Amulya. So how do we quantify the noise level as numerical values and
Okay.
use that supervised noise predictor model? What kind of noise data is used to supervise noise predictor model? Is it Gaussian noise that the noise predictor should generate?
It's again Gaussian noise, because whatever we added was Gaussian, and later we generate Gaussian, and then it's just like when you do addition, and you do addition with these similar terms, you cannot add x and y, because even though, for example, if x is a different what parameter data type and y is something different, you cannot add them. So what we try to do here is get everything down to similar types. For example, tensors. So these noises are nothing but tensors later. I'll explain in the latent space part, where the noise added is all coming down to numerical values, nothing but these tensors. So when you predict the noise and you subtract the noise, everything is in the same format. Uh, that's number, and we'll be using tensors here in order to do the whole process. I hope I answered the question. And if you still have a question, you can always ask. Okay, then I'll.
Yeah, I hope, Bismillah, that question was answered.
Okay.
Bismillah, you feel free to augment if you have any inputs.
Then
No,
I'll.
sure, Vic. Yeah, I would like to see it probably in a little more detail, probably in the code or something.
Sure, sure. Okay.
Okay, so I'll just resume this thing. So I think we understood how the initial image, from the initial image, we're generating another image which is not exactly the same, but sort of similar to it, because you have many losses that can be taken into consideration and what actually happens, and we know it. It's prediction. It's not the actual thing that it predicts. It's, you have just few. It's not always 100% accuracy is what I'm trying to say. Then The sad part is that this is not how the stable diffusion actually works. Because as we know, image space is enormous, and this very simple thing. Just thinking about image justify 1, 2 into 5 and 2 dimension with 3 color channels is red, green, and blue. Overall, it comes down to 786,432. That's 7,086 and 432 dimension spaces. It's just for one image, and you have to do it for multiple images that you generate as you go, which is not feasible and it makes no sense. And many of these, OpenAI's DALL or Imagines, Google's Imagine, they use something called as pixel space, but still this is not enough, is what the sources claim. So what actually came into picture is nothing but something called as latent diffusion model, where we'll be making use of latent diffusion. And this is a very famous image that we would have seen in so many research papers, and the algorithm behind stable diffusion. So this is one thing that actually appears. Stable diffusion makes use of latent diffusion model in order to solve the speed problem that we eventually face. That is because of the enormous space that image takes and not feasible enough computational power and so many such things. So now let's try to understand what these terms actually say and what are these different blocks and how text comes into picture and all of that. So yeah, I think I'll say here. So as I explained before, X is the initial image, is the encoder, and then Z is the dense space information. So basically, this latent space is the place where all your image data gets compressed into latent noise. So, as I again said, tensors. So, whatever those numbers you have will be converted into tensors, and later the whole computation is done, and you'll have your initial image coming back. So this whole the process of denoising, or the process of foul diffusion, that's adding noise and removing noise, everything is done in latent space in order to maintain that very less what storage or anything in terms of that. So just to tell you guys something about, I remember hearing this from my friend, something called as tiny ML, where it seems you make use of 14 KB data storage in order to do computation of ML training or anything like that. So we have to, like, I still have to do a little more research in that domain, but it just struck my mind, and how it's not always you need a very big storage in terms of ML training or deep learning training for these models. It seems you can also do it in these extremely small spaces, and the term is tiny ML for it, but if you're interested, you can look up. Then yeah, coming to how these text
So you are equating this with edge computing. You're
yes,
trying to, run AI models on a very tiny, let's say mobile app or something, right? So you are compressing the model to model weights particularly to
yeah,
run on the edge. Okay, fair.
yes.
So, what is the difference between noise and latent noise? Is there a difference?
Okay, so noise in this, the normal noise that is being generated is not compressed. When it comes to latent noise, it is being compressed and converted into tensors in the latent space. So this is one of the very simple example differences that I can tell as of now.
Okay.
Yeah, uh, coming to understanding the symbols that I already explained before, X, Z, and X bar. Okay, X bar is, by the way, the image that gets generated from the whole process after reverse diffusion. So you can see this block, the yellow one, where the text prompts come into picture. So as of now, we're just talking about how you're putting image input, and later you're doing the noising and denoising and getting back your original image. But what we actually see in stable diffusion is that you try giving a text prompt, and then it eventually produces images. So you're not giving any image input here. But what is actually happening? That's where the clip model comes into picture that I will cover eventually. Um, So yeah, okay, yeah. So variational autoencoder basically in order to help you with the latent space, that is reducing the dimensionality or removing or extracting few uh, parameters that are important and just condensing all of them down or compressing all of them down to this space. So as it says, the latent space is 48 times smaller, so it uh, benefits of crunching a lot fewer numbers. That's why it's a lot faster. So yeah, why latent space, as I already explained, how it can be useful in faster computation or the noise and all of that. Again here. So during training, instead of generating a noisy image, it generates a random tensor in latent space. Instead of corrupting an image with noise, it corrupts the representation of the image in latent space with latent noise. The reason for doing that is a lot faster since the latent space is smaller. Again, it's all about the, that's why even in our normal systems or any operating systems, you actually have something called as cache in between. It's extremely fast in terms of accessing any bit of or any piece of memory in it for the processor. And it actually helps the whole processing or makes the job of producing results faster. So that's where the cache comes, and you can actually call latent space as another version of cache here. Yeah.
So let me understand this right. So you had a image to noise, and then you had the reverse diffusion, noise to image, right?
Yeah.
That was the original plan.
Mm.
Now in latent diffusion, compared to original diffusion model, you
Mm.
convert the image into a latent vector space, which is
Yes.
compressed, and then that transformed latent image, you
Mm.
add latent noise to it,
Yes, sir.
and then bring it back to the latent image and regenerate.
Yes, sir.
So you'll have to apply a VAE on the original image itself to compress the image to the latent space image, and then add latent noise, right? So there will be a VAE on forward diffusion as well as maybe a VAE on reverse diffusion.
Yes, sir. Because it's all done in latent space where you have to deal with compressed data. You have to make
Right.
use of these VAs.
So the advantage of doing this compared to original diffusion,
Yes, sir.
tremendous performance improvement. Huh?
Yes, sir. Yes, sir.
Okay.
So as I told you, there are two methods here in order to get the image output or denoising it. So the first one is unconditioning, where you have an image, and as I told you, you do all the forward diffusion process. You add the or you do the reverse diffusion process in the latent space, and you generate your new image. So here you can see um, in the 199th position timestamp, you had this image of a man or a stick figure with complete noise in it. Then later, after going through these, iterations of removing noise, predicting noise, removing noise, predicting noise, you later generated at the end this faint this representation of the stickman at the end. But eventually, when you keep doing this at every step, you sort of come near to the image that you initially had put at every step, which is a faint representation of the original image, extremely faint. And it eventually gets better as you do this process again and again and again. That is predicting the noise, then subtracting it, predicting, subtracting, again using the Markov chain algorithm or process. So now coming to conditioning, that is the text prompts. So along with the text prompts, when you try doing this denoising, we call this as conditioning, and we'll understand how it is done. So text conditioning, this is the whole architecture where you have text prompts, for example, photo of a cat. Then you have a tokenizer. So we are making use of, or not we, I mean the stable diffusion, where the latent diffusion model, it makes use of clip tokenizer. That is, I think OpenAI has created it, and these make use of such tokenizers in order to in order to understand the or in order to generate images along with text prompts. So we'll understand how tokenizer works. So now you have the text prompt for cat and tokenizer. It's creating few numbers here. So let me just tell you this. If you're feeding anything into your model or anything as such, or even your computer as such, it's all numbers. So as we have studied before, binaries for your system. Similarly, you need numbers for your model. So photo of a cat. Every character or word here gets converted into a number here. 50, 24, 59, 30, 39, all of that. And the tokenizer does this job of assigning each of these words a number, and clip does this job. Let's come here. So contrastive language image pre-training tokenizer, the clip tokenizer. So the text prompts is first tokenized by the clip tokenizer. The clip is a deep learning model developed by OpenAI to produce text description of any image. Stable Diffusion uses this clip tokenizer. So what is tokenization? So it's a computer's way of understanding words. As humans read words, computers read numbers, and read stated. So that's why this tokenization is extremely important. And then feeding embeddings to the noise predictor. Later, you have text to image step by step. Later, I'll actually explain. Okay, now whatever we studied so far with image to image, now we'll try and understand the whole thing with text to image. So, as I already told you, Stable Diffusion generates latent diffusion model uh, generates these random tensors in latent space. So these set of tensors that is created, it eventually gets rid of it by the reverse process and making use of the noise predictor model. And again, the noise prediction is done using unit, and where you have your text prompts also coming into picture. So now it takes the noisy image along with text input and predicts the noise. So if I want to generate an image of where I have text prompt saying a smiley face along with your image which has a lot of noise, and also text prompt of a smiley image, both of them are fed into this unit. And unit also, before it enters unit text prompt, it has to undergo all the processes here, as I showed you. The whole process, that's from text prompting to text transformation. This whole thing is done by clip tokenizer, clip the whole model, and then it enters this noise predictor model along with.
You have text to image, then there
Yes.
is no input image involved, right?
But yes, sir.
So there is why in this diagram why you are showing an image on the left side as being input as well.
So this image, we start from noise. So we take something which is noise. So we cannot tell that whatever we have taken is a smiley face, whatever taken is a cat or a dog or a flower, anything as such. It is just noise. So we take this noise, which is nothing but image representation of latent noise, and we feed into the noise predictor. It's like you're trying to make your new designed cloth, but you don't know what design you want to put. But depending on your customer's uh, um, whatever he has to say, and you just take a piece of cloth, a white cotton cloth, and then you start adding designs to it. So this just for any design that has to be produced, just let's say that white cotton cloth is the starting piece. So this noise image acts as this initial base for anything, and then this text prompts are the ones which modulate or modify the image in order to produce what it eventually asked for.
So you are taking two inputs.
Hmm.
One is the noise, which
Yes,
is the
sir.
left side thing,
Hmm.
and in that left side noise represents a noise related to image.
Hmm.
And then you are taking the text modulation of that. You are modulating that with text prompt or text input,
Hmm.
and then you are predicting noise in latent space.
Yes, sir.
Okay, so this is still the forward diffusion process on this diagram.
No. This is already in the reverse because you're predicting noise here. This image in latent space, which is nothing but noise, already has a lot of forward process, it's already done on it. You already have the 199th or the 200th stage here. That is after getting all the noise. Because you have noise because of that forward process. And then now you're adding the reverse process along with text prompts in order to get your desired image. So this whole noise predictor along with text prompts and including the noise image, everything happens in the reverse process.
So text prompt is only and only applied during reverse diffusion.
Yes, sir, that's what I guess.
Okay.
Then again, the new latent image that we generated is generated by predicting, as I already told, predicted noise and the latent image. You subtract them, you have the new latent image, and this happens here also. So after doing this multiple times, you eventually decode it to your image that you asked for. So now it was photo of a cat, and now you have photo of a cat here. So by variational autoencoders, again, we had seen it before. That is for the latent space. That is encoding and decoding. That is where the variation autoencoders come into picture. And because the latent space concept comes here, we make use of variation autoencoders. Again, the encoder converts an image to a lower dimensional representation in the latent space, and the decoder restores the image from the latent space. That's what it's used for. Now I guess we have almost completed our three different algorithms and how they work in generating such AI images based on text prompts and also on just image prompts. And you have different conditioning also. So now let's understand the applications of these algorithms that's in the SOTA models.
Amulya, can you go back to that main picture that you saw all the components of stable diffusion?
Is it this one?
No, back. Yes, this one. The
Okay.
next one. The next one. Yeah. So in this things we have probably 6 different main building blocks, right? So my first question is, what components of these building blocks are trainable or sort of the model weights are updated, and what part of these components are sort of pre-trained and their weights are fixed?
Okay, so coming to clip and the unit, it is already fixed, I guess, because you're making use of these pre-trained models in order to predict noise. And the whole forward diffusion process is where you're training it. And then in the reverse process, you have clip and unit coming into picture. They're all pre-trained models, and the weights are fixed, as I said, as it was mentioned before in the question.
Okay, yeah. So next, how is the training process? What are the steps? Now, if you say in case of GAN, that is sort of a multi-step approach. For first few hundred iterations, we train only the discriminators, and then we slowly add the generators, and then we do sort of simultaneous training. So in this case, do we take a multi-step approach that we first train the forward process, something like that? Can you elaborate on that?
Yeah, I understood your question. I guess here it is important to take the forward diffusion process initially in order to generate that image, which is nothing but noise. So after that only you can start applying the whole reverse diffusion process here. Which I mean, because after the point in forward diffusion, when you've already started applying the reverse diffusion technique or method, if you still generate images which are producing more noise, it's of no use later, because you've already started your process of reverse diffusion, and you're in your way of coming to this original or nearly near to the original image. So if you somewhere in between start your reverse process and still make your forward process to carry on with its image generation or noise generation, it makes no sense to again come back and apply it to some other step. I hope you're getting. It's like you are making this thing go forward, and somewhere in between you started your reverse process without stopping your forward process. I mean, if you don't stop your forward process, it would mean, I mean, why would you again add your reverse process somewhere here? You, instead of that, you just generate your noise till the end to how many ever steps you want, and then you start with your reverse process. I hope I am right in this thing. I really want some input.
So, Bismillah, there is a good point you brought up. So, in GAN, you train the generator discriminator simultaneously with
Huh.
the cumulative loss function minimization, right?
Yes, sir. Yes, sir.
So, now, Bismillah, the question is in here in LDM, do you train the forward and reverse diffusion in lockstep simultaneous cumulative loss minimization, or you train them in sequence? First, you train forward diffusion model. Once it's done, then you bring in the reverse diffusion as a separate training. Bismillah, any thoughts?
Yeah, I have to read it. I don't know. That's why I asked.
Okay, that was your question. Okay.
Yeah.
I am also thinking that you first train the forward diffusion, let it finish, and then use the output of that to do the reverse training. So the output of that basically becomes the input to the reverse training
Yes.
network. So it's not lockstep like generator discriminator of GAN.
But in
I'm
GAN,
not sure, actually, not sure of that.
but I just a thought that in GANs it's repetitively updating both the models in order to just successfully create a generator model which can completely fool the discriminator.
Yes,
You
precisely.
have this simultaneous parallel updation going on in both the steps, and both of them are learning at the same time. But here you already have like a completely the first step is to generate a noise, and the second step is to denoise it and get back something similar to the original image. So this is what I think, but later I guess
So yeah, it is probably not combined loss minimization.
Hmm.
First you train a forward network and later on you train the reverse network. That's what I'm arriving or guessing.
I think I'll look into it, sir.
Okay. Bismillah, any other questions?
Yeah, one question is how do you calculate the model performance or the loss functions? Is it the loss between the x and x bar?
No, not X and X bar. This happens in the sequence. So there are like multiple steps in between. Okay. So in the forward process, what happens? You're generating these noise, depending on previous images noise. So the loss function when it comes to denoising, again, it's nothing but the amount of noise that is being generated. So it's all dependent on these minute steps or these small steps in between. You don't take X and X bar into consideration for uh, predicting or generating any such things in this whole latent space. It's all these subsequent, steps that are considered in order to calculate the loss or predict the noise or anything as such. But overall loss calculation, I guess you have to do it with X and X bar because those are the,
Do you have the loss equation here?
I don't think I have the loss equation here, but
Okay.
But yeah, if you have to calculate the loss, I guess it's with X and X bar at the end overall. Coming to the SOTA models. So what are these SOTA models basically? They're nothing but what they claim to do is whatever algorithm they are using outperforms almost all the algorithms present. So if can typically achieve performance level, meaning it's like the benchmark algorithms are used by these models. So here we will discuss about stable diffusion, Dalito, and midjourney. But because of the time constraint, and I feel that I have to go to the code demonstration of stable diffusion, I guess I'll stop here. And we have understood the whole functioning or what algorithm stable diffusion uses, that is diffusion model. And now I'll try and show you the code demonstration for stable diffusion. So basically, Stable Diffusion is open sourced. It's code that can generate images. if not the whole the what do you call the network or the model, where in other terms, if you can just see you have these different layers and all of that. It is a transfer learning approach here, where you make use of already trained or pre-trained diffuser model here. So I think I've connected it, and let's just run these uh, or install these dependencies or libraries that we have to use in order to make use of the stable diffusion pipeline. Sorry. Any question? Okay. Now, coming to the diffusers. So diffusers have multiple stable diffusion versions in their pipelines. So we will be using this version of stable diffusion, and we'll be loading it into something called as pipe, which is the pipeline or a model that holds this whole stable diffusion version 1-4. In between, if you have any questions, I guess you can ask, because literally takes a lot of time, because GPU is also, I don't think it's performing that well.
So I had a question. So the denoising, does it have to be again the same number of steps which it has to go through when you added the noise, or can it be actually clubbed and be a shorter version of, like you said, 200 steps you took to actually add the noise, right? So does the denoising also have to be 200 steps, or it can be actually shorter?
So basically, it depends on the image being generated. If you do the same 200 images back, I guess you'll get much clearer image, even if it's not the same. But if you want to drop in between, you might get something different. The image might, but you'll still have some noise in it. The thing is that even the image that is being generated back after denoising is not the pure original image. It is something which has some amount of noise in it. Because of that noise, it looks different. So, I mean, if you ask me, I would say that, well, I've not looked into the whole 200 into 200 steps, but it is always good to have, get back all the 200 steps without stopping in between. Because again, the one which you get back is also not a completely denoised image. It still has noise. That's why it is different from the original image.
Right. The only thing I wanted was basically, since we have trained it from the final trained model, if we could actually, I don't know how to maybe have a better model, which could actually, instead of those 200 steps, which takes a lot of time for denoising, we could have a more compressed kind of a model.
Yeah, I think I'll explain that in Discord if you like.
Okay.
Eventually, you understand that. But again, here we'll just load CUDA here for the GPU purpose. Then takes time. So now coming to the actual thing, there's something called as prompt here again. So here it said a photograph of an astronaut riding a horse. I can still put things like a horse in the grasslands. A horse in the grassland. So let's see, and in one end, let's run it. And so prompt is again what we are passing, and image. So the pipeline, you're passing a prompt to the pipe that or the model that you've created, and image is 0 is basically telling that you're generating an image of just generating just one image. So in order to generate multiple images, you can actually do this, or sorry, 3 or 4. I'll eventually show that. So now you can see that a horse in the grassland has been generated, and let's talk about the resolution and all of that eventually in the the coming codes. Now this is an image, so it just literally feels good to have something being produced. And then coming to this, yeah, exactly. So now you have manual seed here. So we already know if we basically set a seed in any model, it makes sure that the same number of or the same type of numbers or the numerical values are generated every time you make any changes. Similarly, what we do here, or what we try to do here, is that we try to set 1024. So every time you generate an image with this seed, it will eventually generate images of the same type. That is, same image has been generated. So let's just give it a try here, and we'll change the seed and see what else can be generated. See, now you can see that a different image is being generated. If I don't give this thing, or I change the seed to something like, this can be one of the seeds, so let's just try. You saw the image, right? It was something different. And now it's again different. So if I still come back to 1024, by doing this, we can actually, okay, it's a very simple concept that we make use of in machine learning that can also be used here in order to maintain those numbers, in order to generate the names that we want and we want to see all the time when we run it. So see, we got back the same image. Now coming to, I think, yeah, seeds and prompts, it's the same thing again here. I guess this should once again, if you just generate it. Oh, basically 1024, right? So if I'm generating it here, again, it's the same image as above. Is it the same image? No, okay. What happened? 1024. Something similar, but little grass has come here, but I don't know why. Okay, let's see. Right. Then coming back to now generating these images with number of columns and number of rows. They're just given in a code for that. And here, as I mentioned earlier, when you generate more images, then you can make use of this. And yeah, that's not. I think the prompt is something in there, and we can make use of our own prompt. Let's just run this function and also there was this thing where they were talking about a default value for your this generator, basically the manual seed. So by default, the higher the value of the manual seed, the more time it actually takes to generate your images because the resolution comes into picture. Now, if I reduce this to somewhere around 50, which is the default value basically, you'll have something else which might not look as good as what is above. You can actually see the computation being faster than what it was before. Can you see these? It's not that uh, you know well denoised thing, or the image produced is not as good as this image. It literally feels so real, and yeah, but this is not that good. We can see the defects in it. So this is one of the reasons. And coming back to, yeah, you can see it here. I guess, yeah, this was the whole demonstration and stable diffusion. Basically, you can go for more grids here. And yeah, that's it. I think I'm done with my webinar today here. Any questions you can ask? Yeah, thank you.
Yeah, good content, Amulya. So, audience, any questions?
I had one more question. So when you're adding noise to the image, is it just enlarging or decreasing some pixel in that area? Do we have a noise model where we can actually turn the image around or have another view of the image?
Okay,
So
so I understood what you were trying to say, but I guess as I mentioned, we're using Gaussian noise here. So making use of Gaussian noise, we are trying to add noise. So I understood the augmentation perspective. So because we sort of try to change the data set by data augmentation so that it can learn properly by rotating it, by enlarging and doing all of that. But this is not what we do here. We add noise in other terms, basically pixel wise changing it uh, eventually in different steps. That is through Gaussian noise, and it has its own equation and the way it does a mathematical aspect of it. But yeah, coming to what we actually use in order to add noise, it is Gaussian noise.
okay.
Yes, sir. I think I'm done here. Thank you for being there and listening to the webinar. Thank you.
Thanks, Amulya. Thank you, audience, for joining. Look forward to seeing you in the next webinar. We'll share this recording on our YouTube channel.
Yes, sir. I'm open to any inputs or